Hello, so in this video we're going to go over sig figs. So basically how to find the number of sig figs in a number, how to deal with sig figs when adding, subtracting, multiplying, dividing, using exponents, using logarithms, and also how to determine the number of sig figs after square rooting. Anyways, so firstly we're going to go over how to determine the number of sig figs in a number. So in order to do that, the first step would be to determine if a decimal point in that number is present or if it's absent. So what you do, basically, if the decimal point is present, is you start on the left side, and then you start looking for a non-zero digit. So in this case, you start on the left side. The first number is 2, and since 2 is non-zero, it's significant. And every number to the right, so every digit to the right of 2 is significant. So 2 is significant, 3 is significant, 5 and 7, they're all significant, so that gives you 4. It doesn't matter what the numbers are to the right. If the decimal point is present, after the first non-zero digit, counting from the left, everything is significant. So if you look here, we start on the left side, and we start looking for the first non-zero digit. The first digit we look at is this. It's 0, right? So that's not significant. The next one is also 0, which is also not significant. Likewise, the 0 next to that is not significant. The number next to that is 3, and now we have found our first non-zero digit. And as I said, every number to the right of this 3 is significant. So 2 is also significant, which gives us 2 sig figs. The same thing here. We start from the left. The first digit we're going to look at is 2, and since that's non-zero, it's significant. And every digit to the right of this number, 5, 6, and 0, are significant. So that gives us 4 sig figs. So even though this number is 0, since the decimal point is present, it's going to be significant, so that would be 4. So let's try doing the last one. Try doing it, like pause the video or something on your own. So you start counting from the left, right? The first non-zero digit you run into is the first digit. It's 5. So every number to the right of this, 5, 6, and all these zeros are significant. That gives us 5 sig figs. Alright, so that's how you determine the number of sig figs when a decimal point is present. When it's absent, though, you can't start counting from the left side. What you do is you start counting on the right side. So you start counting on the right and look for your first non-zero digit like we did when the decimal point was present. So the first non-zero digit would be 7, and every number to the left of that digit is significant. So in this case, it's 7, 5, 2, and 3. They're all significant, so that gives us 4 sig figs. Likewise, for 5,000, we start counting on the right. So we look for our first non-zero digit. That's 0, so that won't work. That's also 0, won't work. That's 0. And we run into our first non-zero digit counting from the right, and it's 5. And since there aren't any numbers to the left of that, the number of sig figs is 1. So 6,707, we start counting from the right. We look for our first non-zero digit, which happens to be the first digit we look at, 7. And it doesn't matter that this number next to it is 0, since it's on the left, it's significant. These are all significant, which gives us 4 sig figs, right? Now try doing the last one, right? So you start counting from the left, or from the right. You count to the left from the right, right? So hopefully you got 2 sig figs because you look at your first digit, it's 0. Next, it's also 0, that's 0. So you look at this number, and everything to the left, since 3 is non-zero, would be significant, so that gives us 2. Anyways, that's how you determine the number of sig figs in a number. And like, let's say they give you the number in scientific notation, so it would be like 2.57 times 10 to the 5th. So basically what you do is you just ignore this part and you just determine the number of sig figs in this part of the number. So since that the decimal point is present, you start counting from the right. That gives you 1, 2, 3 sig figs. So this has 3 sig figs. And I mean, the same thing, if it's like 1.578 times 10 to the, I don't know, negative 7th, you ignore this part. So you just count the number of sig figs here, the decimal point is present, and we get 4 sig figs, right? Because you count 1, 2, 3, and 4. Anyways, so that's how you determine the number of sig figs. So the next thing would be determining the number of sig figs when adding and subtracting. So let's just start with an example. Maybe 4.357 plus 2.1111, right? What you do basically is you just add it like you would add, a normal number. So 6.4681. And you look not at the sig figs of the two numbers that you're adding, but the number of decimals, so the number of digits to the right of the decimals, so the number of decimal places. So that is 3 decimal places, and that is 4 decimal places. So what you do is you take the least number, so it would be 3 in this case, so the smaller one, and round off to 3 decimal places. So since 1 is less than 5, it doesn't round up. We just drop it and get 6.468. So to do another example, maybe like 5.823 plus 2.57. Actually, let's change that to an 8. If we do that, what we do is we would add it up like a normal number, right? So if we add it, we get 8.398, right? Then we look at the number of decimal places. It's 3 and 2. And since 2 is smaller, we use this number to determine the number of decimal places in our answer. So it should be just 2. And since there is that 8, and 8 is greater than 5, we have to round up. So basically what we get would be 8.40. So we're still keeping the 2 decimal places in our answer from this number right here. Anyways, so maybe let's do an example with subtracting. So 5.83 minus 2.375. So try doing this on your own. The rules are exactly the same as addition. So what you should have got is 3.455, except for the 5 rounds up, and you get 3.46. Because we have to limit the answer to 2 decimal places. Now you won't see this often, but sometimes you might have to subtract or add 2 numbers that don't have decimal places. So like that plus 5, 3, 2, 1 or something. And what you do is you just do the same thing. You just add first. And then since this, and then you start like looking for your first significant digit, and it's starting at the 100th place, right? So it's only, 5,500 is only significant starting at the 100th. So and this is all these numbers here are significant. So you can't write these 2 numbers as significant digits. So what you have to do is you have to change these to 0. And obviously you would round, but since 2 is less than 5, you round down and get 10,800 as an answer. But you won't really see this often. Maybe let's do another example. So like 5300 plus 2.578. Now all these numbers are significant, but this is only significant starting from the 100th again. We can't write any digits that are smaller than 100. So we only can write that, right? So like if you take account of sig figs, adding 2.578 to 5300 doesn't really do anything to the number. Anyways, so that's basically how you do sig figs when adding and subtracting. The next thing would be multiplying and dividing. So multiplying and dividing. And then this is actually easier than adding and subtracting because all you need to do is basically, let's say if we have 2.35 times 8.7. This has 3 sig figs, right? This has 2. So our product will also have 2 sig figs. So you basically just take the smaller one, the smaller number of sig figs, and write that as the product. So if we actually calculate this, what you're going to get is 2.35 times 8.7 equals 20.445. And we can only write 2 sig figs, so we just leave it 20 points. And we have to add the point because if we don't add the point, then it would look like 1 sig fig, right? Because this... Alright, so maybe let's try another one. So 3.8, or like 13.8 times 105.7. This has 3 sig figs, this has 4, so this would have 3 sig figs as well, right? Try doing this on your own and see what you get. So what you should have got is 1,460. So 1,460. And 60 because the exact answer is that. But what you have to look at is you're rounding again. So you look there, that's greater than 5, so you round up and it becomes 1,460. Alright, so maybe like let's do a division example. So if we have 25 divided by 5.0, they both have 2 sig figs, right? So our answer would also have 2 sig figs. If we do that, that would just be 5.0. That's 2 and that's also 2. Maybe 365.8 divided by 27. So try doing this and see what you get. Alright, so as an answer, you should have got something like 13.5481481. Now, if you look here, that only has 2 significant digits, so we can only have 2. So our answer is 13.5 for blah blah blah. But since it's only 2 sig figs, because that one has 4 and that one has 2, and always we take the smaller one, we can only have 2 sig figs. And since there's a 5, we round up. So we round to 2 sig figs and get 14 as an answer. Alright, so the next thing I'm going to quickly go over is how to deal with sig figs in powers. So basically, like, sig figs when raising something to power is like kind of like an extension of multiplication. So I'm only going to deal with powers to like whole numbers, and we're assuming that these powers, so like let's say 3 to the 5th, the 5 is an exact number and it has like an infinite amount of sig figs. Anyways, so like basically what you do is, let's say we have 2.75 to the 26th power. Our answer would be equal to 2.75 times 2.75 times 2.75 ... like basically 2.75 multiplied by itself 26 times. And if you think about it, remember that's just multiplication. In multiplication, determining the number of sig figs and its product, what you do is you find the number with the least sig figs, and that would be the number of sig figs in your product. But in this case, all these numbers have 3 sig figs. So our product will also have 3 sig figs, and if we actually calculate this, we're going to get something like 2.646 2.64636 blah 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 to 2 to 10 times 10 to the 11th. And if you look here, remember we can only have 3 sig figs. And since that's a 6, we're going to round up and get 2.65 times 10 to the 11th power. So in exponents, so when we have an exponent and we assume this is an exact number, so like the 26 is an exact, that means it has infinite number of sig figs. The product would have the same number of sig figs as the base. So like let's say it's 2.7 to the 5th. If you actually calculate that, you're going to get something like 143.4. Since this only has 2 sig figs, our answer can only have 2 sig figs. So this is equal to 48, but remember 2 sig figs, so we're going to round to 140. Just another example, try doing this on your own. 3.02 to the 6th. So how many sig figs should this have? It should have 3, right? The product. So like the answer should have 3 sig figs because that's 3. And therefore our answer would be 759. So hopefully that's what you got. Alright, so the next thing is a square root. Okay, so let's say we're taking the square root of a number. So it'd be, let's say 8.9. This has 2 sig figs, right? 8.9 has 2 sig figs. And so our answer will have 3. So it'd be like 2.983, but since 3 is smaller than 5, we're just going to drop it, and our answer will be 2.98. So basically, if we have a number inside a square root, so let's say if the number of sig figs of m is equal to 1 plus the number of sig figs of n. Alright, so the last thing we're going to go over is logarithms and exponents that aren't like whole numbers. If we have log, 100, for example, then we just write this as, like the answer is 2 obviously, because 100 is 10 to the 2nd power, but we have to write 2.0 if we want to include sig figs, because 100 has 1 sig fig, but we have to write 1 decimal place for the answer. So let's say, so like a general formula, I guess. So if it says log n equals m, the number of sig figs in n is equal to number of decimal places in m, sorry. So that would be log 100, like for example, let's say log 238. So let's try doing that on your own and see what you get. So you should get something like 2.3765. Now, since this has 3 sig figs, our answer should have 3 decimal places. So we leave it as 2.377. Hopefully that's what you got. So this isn't just for base 10. So like when I say log, it's base 10, right? It could also work for like literally any logarithm. So let's say like ln 38. So the answer for that is also like the number of sig figs in 38 should be equal to the number of decimal places in our answer. So if we get ln of 38, the answer is equal to 3.637. And since this has 2 sig figs, our answer should have 2 decimal places. So we write 3.64 because it's actually 3.637, but we round up because we have to have the 2 decimal places. Okay, so the final thing we're going to go over is exponents. So in exponents, that would be like, we already went over things like 2.75 to the 6th power, where 6 is an exact whole number with infinite amount of sig figs. The difference here is like we're going to do numbers such as like 10 to the negative 7.85 or something, right? So if we see this exponent here, it has 2 numbers after its decimal point. Therefore, our answer is going to have 2 sig figs. So it should be 1.4 times 10 to the negative 8th. So 2 sig figs. So to sum it up, the number of decimal places in the exponent is equal to the number of sig figs in answer. So hopefully that makes sense.